All right, now that we've learned about the Lorentz transformation and how to transform from one frame to another, taking into account the postulates of special relativity, let's see how we now add velocities. So in particular, let's suppose that I want to transform, say, a frame of a moving vehicle, a car, S prime, to a frame S, say, along the side of the road. Or perhaps as a better example, the frame of a rocket transformed to the reference frame of the Earth. So, in other words, we throw a ball forward from the moving vehicle. We're going to call that velocity u of x prime, not to confuse it with v, the velocity of the moving frame with respect to the frame that we consider at rest. So that frame's moving at speed v, but within that frame s prime of a moving vehicle, a ball is thrown forward with velocity u of x prime. How do we transform this using special relativity? Well, let's start with the Lorentz transformation. Let's consider Lorentz boost from frame s prime back to frame s, that is going from x prime to x. So we learned in the Lorentz transformation that to go back, we have x prime plus vt prime, basically the Galilean distance adding velocity times time of the frame, but then multiplied by this relativistic factor gamma, right, the 1 over square root 1 minus v squared over c squared. And now let's take a differential of this. That's kind of like taking a derivative or taking small displacements in the quantities that vary, x and t. So we're going to do a dx, and that's going to give us gamma times the quantity dx prime plus v dt prime. Okay, so small displacements in x prime and d prime. Likewise, let's take the equation we learned for the transformation of time. Remember, time is not universal. And we had this other equation to get the time in the unprimed frame. It's gamma times the quantity, the time in the prime frame, t prime, and then mixing up a bit the space component, vx prime over c squared. Taking a differential of that, we get dt equals gamma, and then I have dt prime plus v dx prime over c squared. All right. Now, to get a velocity, or at least the speed, ux prime, and then get that in terms of ux, why don't we take the ratio of these differentials, dx over dt? So let's do that. Dx over dt would be what I call the velocity as measured in the unprimed frame, s, and that's just the ratio of these two expressions. This expression here for dt over that expression for dx. Actually, the other way around. dx over dt, excuse me. Okay, so here's the gammas will cancel, and so I'm going to have dx prime plus vt prime in the numerator, and then in the denominator dt prime plus v dx prime over c squared. And now what we can do is divide both numerator and denominator by dt prime. That'll cancel the dt prime here in the numerator, leaving just v, and that'll give me dx prime over dt prime in the numerator. In the denominator, I'm also dividing by dt prime, so this dt prime cancels and becomes 1. I have the v over c squared, and then this dx prime becomes dx prime over dt prime as shown here. And that's going to give me then this equation, u of x is u of x prime plus v, because that's the definition dx prime over dt prime, divided by 1 plus v over c squared u of x prime. That is how now velocities transform from one reference frame to another, taking into account special relativity, at least for velocities along the direction of motion. Okay, so let me summarize in the next slide here. Summary here. So we just worked out by taking differentials of the Lorentz transformation equations that the velocity in one unprimed frame is that in the prime frame plus the speed, relative speed of that frame relative to the unprimed frame, divided by the quantity 1 plus v ux prime over c squared. But this is the parallel component. This is the transformation of velocities along the direction of motion of the frame, or the two frames. What about the perpendicular components? Well, we didn't work that out. We wouldn't have this addition plus v because those are transverse to the direction, so you might think those velocities are unchanged. However, keep in mind that the time is changed. There's a time dilation factor, or at least the Lorentz transformation factor for time, which comes in the denominator. So in the transverse direction, uy is uy prime, but then divided by this expression here, gamma times the quantity 1 plus v ux prime over c squared, where again, gamma is 1 over the square root 1 minus v squared over c squared, and v is the velocity of the frame relative to another. Likewise, the component for uz looks very much the same because it's a transverse direction too, because we're considering Lorentz boosts along the x-axis. So it looks the same, just replacing uy prime with uz prime. But the ux prime stays in the denominator, okay, because that's along the direction of motion of the two frames, and that's where the time transformation equation comes into play. All right, so those are how you would add velocities in relativity. It's a bit more complicated than for Galilean transformations. And now let's do an example. Okay. Oh, yeah, just to say, these were for the perpendicular components. So let's do an example. Let's consider a spacecraft, a great one, right? It's going to go at 60% the speed of light from Earth. And it launches a projectile forward with a relative velocity of 0.8 times the speed of light forward. So, you know, we're getting like into some sci-fi example, right? We've got a very fast-moving spacecraft. It's going to launch another projectile forward at 0.8 c. And what is the velocity of the projectile from Earth, as viewed by Earth? All right, let's consider a Galilean transformation. What would we get? Well, the spacecraft was traveling at 0.6 c. It threw forward another object with a relative velocity of 0.8 c. So relative to the Earth, it would be 0.6 c plus 0.8 c, which would give me 1.4 times the speed of light, which is obviously larger than the speed of light, right? Because the velocity is just added, as we learned at the very beginning of this unit. Let's look at the Lorentz transformation. Well, going back there, we would have had the sum of those velocities in the numerator, but we had that correction in the denominator, 1 plus vux times v over c squared. So the c squared cancels, and I have 0.6 times 0.8 plus 1 in the denominator. That's going to correct the 1.4, and I'm going to get 0.946 c, and guess what? That's less than the speed of light. And this is what's sort of interesting. You can do this for lots of examples. You could set that projectile to be 0.999 times the speed of light, and your sum, your addition of velocities, will always be less than the speed of light in the relativistic case. It's like it really is a barrier, and it is. And you can just go ahead and try it by the examples, but we basically find that when you add velocities in relativity, the resultant sum is always less than that of the speed of light.